Hey, welcome to The Explainer. Today, we're going to tackle that big buzzword you hear absolutely everywhere, machine learning. But we're not going to do it with a bunch of complicated code. Nope. We're going to do it with a single incredible story from history. So let's just jump right in. Here's the big question for today. Could a machine, just by looking at the passenger list from 1912, actually figure out who is most likely to survive the sinking of the Titanic? It sounds like science fiction, right? Well, to find out, we're going to treat our machine like a modern-day digital detective. All right, so here is our challenge. We've got our hands on the actual passenger manifest from that night. The goal is to build what we call a model that can learn the hidden patterns in that list to see if it can predict who lived and who died. Now, every good detective needs clues to solve a mystery. And for a machine learning model, those clues have a really simple name: data. That's it. It's just the raw information that our machine is going to learn from. And this is what's so cool. This is what our model actually sees. It doesn't see names or personal stories. It just sees neat rows of organized information. Things like passenger class, their sex, their age, and then that final crucial column, survived. See that? A 1 means they survived, and a 0 means they did not. So these individual clues, the passenger class, the person's sex, their age, they have a special name in the world of machine learning. We call them features. Just think of them as all the different pieces of evidence our digital detective is going to examine. In that final column, the answer that we're trying to predict, that's called the label. You can think of the label as the answer key. It's literally what we use to teach the machine what a correct prediction even looks like. Okay, so we have our features. Those are the clues. And we have our label. That's the answer. But how in the world does a machine actually learn to connect the two? Well, it does this through a process with a pretty intuitive name: supervised learning. And honestly, the best way to think about this is to imagine teaching a child. You don't just give a kid a bunch of blocks and hope for the best, right? No, you show them examples. You say, this is a red square, this is a blue circle. You give them the answer. A machine learns in almost the exact same way, by studying thousands of examples where we've already given it the correct outcome. So the whole thing really boils down to this simple 3-step process. First, we feed the machine our data, the labeled examples. Then, the machine sifts through all of it, finding all the subtle patterns and relationships between the features and the label. And finally, once it's learned those patterns, we can give it brand new data it's never seen before, and it can make its own prediction. Now, with this kind of learning, you're usually trying to answer one of two kinds of questions. The first is called classification, and that's all about predicting a category. Yes or no, survived or died. Our Titanic problem is a perfect example of classification. The other type is called regression, and that's when you're trying to predict an actual number, like what will a stock's price be tomorrow. But what happens if you don't have that nice, clean answer key? What if all you have is just a giant, messy pile of data with no labels at all? Well, it turns out machines have some pretty clever tricks for learning in that situation, too. This is called unsupervised learning. And here, the goal is totally different. It's not about being right or wrong. Instead, you just unleash the machine on the data and tell it, find the interesting patterns, find the natural groupings. It becomes less of a predictor and more of a pure pattern finder. A really common way this is used is something called clustering. So imagine you give a machine all the shopping data from a website. Without any instructions, it might start grouping customers together into natural clusters. Like bargain hunters or weekend shoppers, just by finding similarities in what they do. It's exactly how services recommend things to people like you. And then there's this third really cool type called reinforcement learning. And this one is all about trial and error. It really is like a baby learning to walk. The machine or the agent tries an action. If that action gets it closer to its goal, it gets a reward. It literally learns by doing. This is the secret sauce behind AIs that can master complex games, and it's even used in things like self-driving cars. Okay, but let's get back to our main event, the Titanic mystery. We took all that historical data, our features, and our labels, and we fed it to a supervised learning model to see what it could possibly find from that single night over a century ago. And pretty much instantly, the model found an incredibly strong signal in the data. A person's sex was a massive predictor of survival. Women had a staggering 74% chance of surviving, compared to just 19% for men. The whole women and children first protocol wasn't just a story. It was clearly visible in the data.
But our model was smarter than just looking at one thing. It was trained to weigh multiple factors at the same time. Not just your sex, but also your ticket class, how big your family was, all to create a much more complete and nuanced prediction. So after training our model on some of the data, we held our breath and unleashed it on a part of the passenger list it had never, ever seen before. And the result? It was able to correctly predict who survived and who didn't 77% of the time. That number, 77%, is what we call its accuracy score. It's the report card for our digital detective. And think about that for a second. Making the right call for more than 3 out of every 4 people using just a few columns of data from 1912, that's pretty amazing. It's a perfect example of finding a clear signal in some very old noise. So here's the big idea I want you to walk away with. This exact same process, feeding a machine features and labels to find patterns, is being used right now, everywhere. It's helping to spot diseases in medical scans, it's powering the algorithm that suggests what you should watch next, and that kind of leaves us with one final, pretty mind-blowing question. If a simple model like ours can see the patterns of a century-old tragedy so clearly, what invisible patterns are the far more advanced models of today discovering that are shaping our world right now?